Hello! This video will show you how to control DC and servo motors using the Raspberry Pi and a joystick. Knowing how to control motors is foundational to robotics, and you can use the approach I will demonstrate to build mechanical devices such as remote-controlled vehicles and robotic arms. Let's start with the circuit. The MCP3002 chip is an analog-to-digital converter which converts the voltage provided by the joystick to a digital value between 0 and 1 for each joystick axis. I use a standard joystick available in typical electronics kits, but I replaced the angled headers with straight ones using a soldering iron. This allows placing the joystick flat on the breadboard. The AL293D chip is a bidirectional motor controller, which allows controlling the speed and direction of up to 2 standard DC motors. I use a small propeller so you can actually see the motor movement. I use a standard DC motor which only has 2 pins for 5V power and ground. A servo motor is simple to use as it does not use a controller chip. This SG90 servo model has 3 connector wires. Mine has red for 5V power, brown for ground, and orange for angle control, but these colors vary between manufacturers. This project requires an external power supply as the Raspberry Pi cannot power motors directly. This power supply will provide the breadboard power rails with 5 and 3.3 volts. The power supply and the Pi need to share the ground, but the Raspberry Pi 5V and 3.3V pins must not be used here at all, otherwise the power supply will backfeed the Pi and damage it. The MCP3002 analog-to-digital chip uses the SPI protocol, which needs to be enabled on the Raspberry Pi if you want to use the hardware implementation which provides the best performance. Time to write some code. Here's a standard skeleton program which I use for most of my Raspberry Pi projects. Such code gives me basic program layout and it handles typical program exit scenarios. The GPIO0 library provides the simplest programming model for this type of project as it has built-in classes for my ADC chip and both motors. I will define 2 instances of the MCP3002 class, one for each of the analog inputs. Input 0 will be used for the DC motor, which I'll implement now, while input 1 will be used for the servo, which will be implemented in the second half of this video. Let's call the motor fan since it has a propeller. The motor needs 2 GPIO pins as it will be operated in 2 directions. The Pi will generate pulses or varying duty cycles, which will be processed by the motor controller chip to provide the power to the motor. If you are interested in a detailed explanation of pulse width modulation, I have a dedicated video explaining it. I want to use the joystick to control the motor direction and speed, where the motor rotation will be following the vertical position of the joystick. The motor source property will continuously obtain the joystick value provided by a generator function. I will write the run fan function in a moment, but I need to take care of some housekeeping first, as the components used need to be deactivated correctly on program exit. Let's write the run fan function now. As I mentioned already, the joystick position is a float value between 0 and 1, with 0.5 being the neutral position of the joystick. GPIO0 motors require that value to be between -1 and 1, so this function will need to perform a simple calculation to interface the joystick with the motor directly. The yield keyword will return the value every time the motor calls for it, which happens automatically with the source property. Let's test it. The fan blades rotate with varying speed according to the joystick input, and the motor stops when the joystick returns to the neutral position. However, the motor makes a buzzing noise in the neutral position, trying to rotate very slowly. This behavior is due to joystick drift, where the joystick value fluctuates slightly in neutral position. Drift affects all analog joysticks. You can see that if I temporarily display the joystick value to the terminal. It looks like mine drifts between 0.46 and 0.54. drift needs to be compensated, and the simplest method relies on rounding the drift range to the middle value of 0.5. I will write a simple function that will take care of that. I do see that on occasion my joystick drifts past the current parameters, so I need to widen the compensation range a bit. Your joystick may go even wider, but I would not worry about loss of input sensitivity here. Even a small motor has inertia and would not be able to start within the drift range anyway. Let's move on to the servo motor. The servo is controlled using a modulated signal similar to the one used with a DC motor, but the servo movement is different. Most servos do not rotate 360 degrees, but have the range limited to 180 degrees. As before, I need to properly deactivate the servo on program exit. Setting the servo source property to none will decouple it from the input. I will also return the servo position to the middle. The small delay gives the servo time to get there before the program exits. In a basic sense, the servo driver function can be identical to what I used with the DC motor. The only difference is the analog input. Here, input 1 refers to the horizontal axis of the joystick. That works okay, but the servo moves only about 90 degrees. Each servo is different, so the GPIO0 library is very conservative with the default range of movement. You need to always calibrate your program to the specific servo used by providing the minimum and maximum pulse values. Most of the SG90 servos I have used work well with the values you see. If you find that your servo tries to move too far or does not quite have the range you want, you would need to adjust these values slightly up or down. This works well, and such approach would work in a remote-controlled vehicle where a servo would be used to steer it. But what I want is to use a joystick to control a robotic arm. In such scenario, the arm should stay put when the joystick is released, and the speed of movement should be proportional how far the joystick is pushed. Let's change the program for such scenario. The servo arm movement will be determined relative to the current servo arm and joystick positions. Adjusting these values slightly up or down will make the arm move faster or slower, but the value ratio needs to be 2:1 for the left and right movement ranges to be symmetric. This function will pass the new position to the servo, but it's possible that it will fall outside of the -1 and 1 valid range, which will produce a runtime error. An added if statement will take care of that by rounding the new position up or down as needed. That was great. I'm able to control the speed of the servo arm movement, and the arm stays put when the joystick is released. As you can see, controlling motors with Raspberry Pi is very simple. There is a small problem though with the control signal. By default, GPIO0 library uses a software-based signal which is subject to jitter. This is different from the drift. It happens across the entire movement range, not just in neutral, and it largely depends on the overall Raspberry Pi system load, which is unpredictable and it cannot be compensated for. This was not really visible with the DC motor, but the servo shows that flow very clearly. You can see the arm moving slightly back and forth continuously. You can always get an add-on board for the Pi to get the stable hardware pulse width modulation signal, but Raspberry Pi is capable of generating them on its own. You just need to use a different software library. Only a minor adjustment to the program is needed. GPIO0 is actually an overlay over other libraries, with the default being RPi GPIO, which can only generate software PWM, and the recommended sub-library for stable PWM pulses is Pi GPIO. Switching to another sub-library with GPIO0 is accomplished by providing a non-default pin factory. This program as is will not run yet successfully. Pi GPIO library communicates with the GPIO pins through a server daemon which needs to be enabled. This daemon in turn relies on remote GPIO, which must be enabled in the Raspberry Pi configuration. You can start and stop the PyGPIO daemon as needed, or disable it permanently. I will use mine temporarily, as I do not want this daemon to interfere with other programs that do not use it. The server is now jitter-free. The best part about using the PyGPIO library is that you can split a project across separate Raspberry Pi systems. This way, you can have the controller in your hand, while the motors are part of a Raspberry Pi vehicle operated remotely through Wi-Fi. I explained the remote access in another video, and I highly recommend that you check it out. That is all for this video. Please give it a thumbs up if you liked it and subscribe. Thanks for watching.